Hello and welcome to this video inspired by a viewer question on the impact of third-harmonic generation on the line width of a laser. The question here is, if we have a laser with a certain carrier frequency and a certain laser line width, and we launch that into a medium where it undergoes third-harmonic generation, what's going to be the line width afterwards? Is it going to stay the same? Is it going to decrease? Or is it going to increase perhaps? Let's try and find out. First of all, let's begin by doing a little thought experiment. Let's imagine that we take a perfectly ideal laser with zero line width and launch it into a medium where it undergoes third harmonic generation. Now, if the initial frequency is 99 terahertz, it's going to generate a new line over here at 297 terahertz. If we then turn that one off and turn on a different one with a carrier here at 100 terahertz, it's of course going to generate a line at 300 terahertz. And similarly, if we launch in one that is at 101 terahertz, it's going to create a line over here at 303 terahertz. So the point is that if we start out with this, let's call it the initial spacing of 2 terahertz here, we're going to create a total spacing in the end of 6 terahertz as all of these frequencies get tripled individually. Now we can use this little thought experiment to conclude that we expect the process of third harmonic generation to generally increase the laser line width, but we can't exactly conclude that it's going to increase by a factor of 3 because essentially what we've done here is take the nonlinear effect and apply it 3 times separately, and then add together the results. But that's not necessarily the same as having all 3 frequencies present simultaneously, and then applying the nonlinear effect. In fact, this is in some sense what defines a nonlinear process. If there is a difference between applying it sort of to distinct elements and then adding together the results, and that's different from adding together the elements and then applying the effect, the process is nonlinear. So we have to be a bit more careful here. I think it would be helpful to start by actually defining what we mean by phase noise. Now, first of all, here we see a perfectly sinusoidal wave that's totally ideal with zero phase noise. And you can see that it oscillates at some kind of carrier frequency. And you can see that each cycle sort of starts and ends at the same place. It's sort of perfectly identical every time we go through one cycle. But if we have a wave where some sort of phase noise is present that changes the phase over time, on top of the oscillation from the carrier, of course, you can see that sometimes the wave sort of arrives a little bit earlier than expected, and sometimes a little bit later. And in total, that's what gives rise to the phase noise. In some sense, you can see that this first cycle here sort of arrives a bit early. So there's sort of a miss time right here. And that leads to a change in the phase of the wave. And if we then sort of repeat the process for the next one, and it's a bit easier to see if we sort of slide them over like so, we can see the next wave here arrives a bit later. So it corresponds to a decrease in the phase. And if we keep repeating this process for every single cycle that we go through, we can build up this map of how the phase basically changes over time. Now, in principle, phi of t here, which is what we use for encoding the phase noise so far, could be any kind of arbitrary function of time. For example, it could also be used for, let's say, encoding the effect of external phase modulation on the wave. You could, for example, imagine you do an experiment inside of a laboratory where there's 2 components to this phase modulation. There's both one from like an actual electro-optic phase modulator that you use to impart some kind of signal on the wave, but there could also be like a very, very slow change in the phase over time because maybe the air conditioner in the laboratory is like cycling on a scale of like 1 day. So that's also including like a really, really slow change in the phase over time. So a lot of different effects could actually take place. But what we want to figure out is how would phi of t actually look if we only look at sort of the inherent properties of a laser. So first of all, let's begin by just factoring out this carrier frequency here because in some sense it's kind of predictable. We don't really care about it. It's the really interesting thing here is the phi of t. So let's just look at the envelope of the field like so. Now, it turns out that a really good model for phi of t that's generated by an actual sort of realistic laser is actually just a random walk in the phase domain like so. And you might be wondering why a random walk would be a good model for the evolution of the phase of a laser. And I think the simplest explanation here is that stimulated emission, which is what generates lasing in the first place, is fundamentally a quantum process, which, at least as far as we know at the moment, is a totally unpredictable process. So basically this means that even though you know the phase at any given instant, and you know all the phases that were present in the past, that doesn't really tell you anything about how it's going to evolve in the next time step. It could go up, it could go down. You really have no way of predicting it because of this fundamental quantum unpredictability. But in any case, what we want to figure out is how this sort of random phase evolution gives rise to a laser line shape. So what we could do is take one of these phase walks, plug it into the exponential, compute the Fourier transform, and then take the absolute square in order to get the power spectrum for that corresponding phase evolution. And if we do that just for a single random walk, we'll find something that looks a bit like this. you can see that it has sort of an approximate like sort of hill shape here, and then a bunch of like spikes because of the randomness. And in some sense, like this is okay, like it tells us something about the width here, but it's also in some sense kind of uninformative, because this is just the shape we got out from a particular random walk that was chosen completely arbitrarily. But what we're really interested in is seeing what happens to this power spectrum as we take the average of many random phase walks. So if we somehow average this together, we are going to get like a smooth curve, and of course we can do this numerically as I've done right here. But a more interesting question from a physics point of view is to see if we can somehow predict the sort of smooth behavior of the average spectrum here, just from the fact that phi of t is a 1D random walk. So is there some way to do that? It turns out the answer is yes, and we need something called the Wiener-Khinchin theorem in order to show that. Essentially, it states that the power spectrum of a random process, which is what we're interested in finding, is equal to the Fourier transform of the autocorrelation of that process. And you can see the same thing written down here in sort of math with integrals and Fourier transforms. Now, there is a proof in the description of this theorem here. I'm not going to go through it at the moment. I'm just going to give you like an intuitive picture of why this might make sense. So why would there be a relationship between the autocorrelation and the power spectrum? The point is that if we have some kind of random process that changes fairly slowly over time, we can sort of imagine that it doesn't have any high frequency components because it's changing slowly. That would expect us to, or that would cause us to expect to have a spectrum that's very narrow, since there's no high frequency contents. But if we take the autocorrelation of this signal, and you have to remember that the autocorrelation basically takes the initial signal and then a copy of it and sort of slide them relative to each other in order to see how different they become as a function of how much you sort of change the time delay between them. And of course, if this signal changes very slowly in time, you have to cause a really large time delay in order for any kind of significant difference to arise. So we expect the autocorrelation to be quite broad in this case. And of course, if we take the Fourier transform of a very broad function in the time domain, we're going to get a very narrow thing in the frequency domain. One of the reasons why we can't just, I guess, mathematically directly take the Fourier transform of a random process is that the Fourier transform isn't necessarily defined for something that is a random process, but we can actually take the Fourier transform of this autocorrelation on average. Anyway, it's kind of math details, but I hope you get the picture of this. Oh, and of course, correspondingly, we can look at a high frequency, or rather a random process that changes very quickly, and sort of draw the same conclusion that the autocorrelation must have a very short duration, because you don't have to slide the signal very far in order for a big change to arise. And if you take the Fourier transform of a short signal here, you're of course going to get something broad in the frequency domain. So anyway, with this in mind, we can basically say that the autocorrelation for the process we're interested in, which is the random phase walk, will just be the integral of this exponential right here. Now, one thing I want to highlight here is that the phase evolution here is going to look a little bit Gaussian in the phase domain. So what I mean by that is that if we take, let's say, 100 random phase walks I've generated right here and just center them on 0 to make things a bit more clear, we can see that as time progresses, the possible range of values that this phase can take on becomes broader and broader and broader the further we go forward, both in the forward direction but also in the backwards direction. So if we sort of take 3 slices of this process at different times, we can see that if we take the log of the probability density, it sort of looks a bit parabolic, indicating that this process sort of broadens as a Gaussian as we move forward in time. And it turns out that's kind of a fairly well-known fact about random walks, that they can be described by probability density whose variance increases in time here. Or you can think of it as the increase of the number of steps that we take. Note, by the way, that the variance is proportional to the square of the step size here. That's going to be important in just a moment. So anyway, the point is that to compute this autocorrelation, we can either do this integral here over this random process, or simply find the expectation value of the exponential of a standardized random variable taken from this sort of standardized Gaussian distribution, and then scaled by b and added on to this number here, a. Now, it turns out that the expectation value of this, I guess it's called the log normal distribution, is just equal to e to the a plus b squared over 2. So the point is that instead of evaluating this integral here, we can just sort of think about computing this expectation value and then plugging into this expression here. Now, first of all, we can assume that a is equal to 0 because we're sort of interested in the phase evolution and we don't really care about any sort of constant phase offset, so we can just ignore that. And the question is then, what factor should we scale b by in order for be set to sort of follow the same probability density as the one shown on the previous slide. And the obvious answer is just that you have to scale it by this quantity right here, which is just the I times the square root of the variance, or rather the standard deviation. So the point of all this is that if we plug this into the expression up here, we simply get that the autocorrelation as a function of the delay is proportional to this kind of exponential that decreases both in the direction of earlier times and the direction of later times. And of course, if you take the Fourier transform of this, you're going to get a Lorentzian curve shape out, like so. Note, by the way, that gamma right here is the full width Hall maximum of this distribution, which you also might refer to as the line width. Note also that this is going to be proportional to the square of the step size. So just to take an example of this actually working out, here I've generated a large number of random phase walks, taken the exponential, computed the Fourier transform, and computed the absolute square, and then averaged all of those things together in order to generate the gray data here. And superimposed on that, we see this red curve, which is the theoretical Lorentzian from the previous slide. Note, by the way, that right here I'm not fitting a Lorentzian to the data. I'm actually generating the data and averaging it together, and then plotting the theoretical curve on top of it. So you can see that this process of having a 1D random walk really does lead to an average power spectrum that is Lorentzian in shape here. And over here we just see the same thing on a log scale. And of course I've linked to a Python notebook in the description that explains this in more detail. You can play around with that if you want. But let's return to the original question of third harmonic generation. If we, just for simplicity, consider second harmonic generation first, we know that the second harmonic generation field is proportional to the square of the incident field. And of course, squaring the phase noise will simply cause us to basically double its amplitude, like so. So just give you an example, it's kind of how it looks for just a single random walk that's been doubled due to second harmonic generation. And of course, if we look at the possible evolution right here, we can see that it gets quite a bit broader if we look at the second harmonic generation result right here. And in fact, it doesn't just simply double, it actually becomes a bit larger than that, as we'll see in just a moment. So essentially, if we go through the same steps as before of computing the autocorrelation, we'll basically find that the new autocorrelation has a decay constant that is 4 times larger, because we've doubled the step size of the random walk, which when you square this becomes a quadrupling of this constant here. And so in the end, the line width will also become 4 times larger, like so. And it's kind of interesting that the process of doing second harmonic generation doesn't just simply double the line width, it actually makes it 4 times wider, like so. Now, I will link to some papers in the description that also explain this in a bit more detail, and do encourage you to check those out as well. So, back to the original question. Essentially, the answer here is that if the phase evolution of the laser can be described by a random walk, which it very often can, then the power spectrum will be a Lorentzian. And if you let it undergo third harmonic generation, you're going to get a Lorentzian out with 9 times the width of the original signal. And of course, in general, if you're undergoing, let's say, n harmonic generation, you'd expect it to basically produce a Lorentzian with a width that's n squared larger than the original one. Another kind of interesting way to think about this is that if you compute the, let's say, the quality factor for the oscillation at the beginning, that's really going to be the actual frequency of the wave divided by its full width Hall maximum, or it's going to be proportional to that. And then after undergoing n harmonic generation, it's going to be n times smaller than the original one, because even though you increase the carrier frequency by a factor of n, if you make the width n squared times larger, overall that leads to a decrease in the quality of the oscillation. So I hope you found this video interesting. Feel free to check out some of my other work over here, and stay tuned for more. Bye bye.